Hi, so today we're going to have a look at transmission diffraction gratings, which lead on very well from Young's double slit. So what are diffraction gratings? Basically, they're a material that's transparent to light, so light can pass through them, and they've got very many vertical, thin, equally spaced parallel lines. Okay, so it's like the double slit. We could see there was two slits there. This is a lot of them together, and they're so close together that you can't really see them. So you can see below on these images down here that you can't really see vertical lines. That's because they're so closely spaced together. And there's about 2,000 to 10,000 of these lines per centimeter, every 1 centimeter. All right, and basically the whole point of these things is if we shine light through them, we get this pattern as shown down the bottom here. So all we have to do is pass some light through a diffraction grating. Now, if we pass monochromatic light here, so this is monochromatic, and it's obviously green, we see this pattern here with the individual bands. And as we go out, the intensity drops. They get a bit darker on the outside, brighter on the inside. And down the bottom, we can see what happens when we shine white light through there. We've got the white band in the middle. And as we go across, we see the white light is separated into its individual colors, but we'll talk about that later. All right, so these maximum, we're going to label them similarly to what we did with the Young's double slit. So we call the first one in the middle m equals 0. That's referring to this vertical line here. Okay, the next one we're going to call m equals 1, and then 2, 3. These are all m equals. And on the other side, we're going to do the same thing, 1, 2, 3, because it's a reflection. All right, so one of the the most useful thing about transmission diffraction gratings is we can analyze different spectra of light. Okay, so we saw on the previous slide this image here where we've seen separation of green light and then separation of white light. Now, what it's really useful for is if we've got a mixture of colors and we want to see what those colors are made up of. So you can see down here on this image on the right hand side, we've got a combination of red and blue. So if we shine that through a single slit, we remember to do that. We do that to make it coherent through a single slit, and then through a diffraction grating, we see it separate into the specific colors, and we can see here we've got a combination of red and blue, and then we see the individual red band and the individual blue band. Okay, we can see those separate really nicely. And why that's useful is because we can analyze things like our stars, the sun, and depending on the colors that are shown, if you pass it through a diffraction grating, that shows us what materials are being burnt and what's producing the light. So it's really interesting for the analysis of what makes up a star. So again, this is what happens if we have some kind of a light source that we don't really know what's a part of it, and we put it through a transmission grating. What we see, our pattern, you can see labeled B down here, is we can see the individual types of light that are comprise this beam that we're sending in there. So you can see there's a lot in this band. There's a lot of green, blue, yellow, a lot of blue, violet, and indigo, and a little bit of red and orange here. But each of these specific lines usually relates to like a chemical that can be found in whatever we're analyzing, and it's really, really useful. So the whole point of this is we separate one beam of light into the colors that make it up. So what happens for a white light pattern? Basically, white light contains the entire spectrum from red all the way down to violet. When we view this through a diffraction grating, the colors get separated out, like we saw with the blue and the red, but all the colors get separated out. We can see the whole range. Violet's the shortest wavelength, so it diffracts the smallest angle, okay? And the largest angle is going to be for the red, and everything else is going to be in between that. And basically, because we get the bands with the one color, we get the bands of spread as well. So we have a look at this image in the bottom right. I might just make that a little bit larger. What we see is that we've got our diffraction grating here, and we've shined our white light through there, and it gets bent. So in the first band, none of them get bent, and they go to a central 0, and we just see a white strip, as you can see over here. Now, in the first band, we see the violet is bent the least, and the red is bent the most. So we're seeing this first pattern here. Okay, we can see we're separating out the light, and then there's going to be another band it's going to be a little bit wider, and we can see that's true here. And as we go further out, they start to overlap. So you can see this one here overlaps here, and that's exactly what we see on the image. So we can actually see the whole spectrum of white light, but really the middle band and the first band, this one here, are the most interesting. All right, so why do we see these really bright spots? Basically, it's because of the very thin slits. They allow the light to overlap, but only at specific angles. And we produce really intense maxima at these angles. So where we see this maxima, that's constructive interference. And basically all the rest of it, where we see the black or where we see nothing, that's total destructive interference. That's just because of the setup of this thing. Yeah, so basically we see some really fine bands, some just individual colors pretty much, separated by nothing, basically zero intensity, unless we're looking at a spectrum of white light. So from this, all of this, we get an equation, and it's as shown here, d sine theta equals m lambda. We have seen this before with the double slit, but it works again. Basically, d is the distance between the slits in the transmission grating. Theta is the angular position of the whatever maxima we're talking about, and m is the maxima. So this is probably the best image I've got of this, and unfortunately it's a little bit blurry, but basically d is the separation between those slits. Theta is the angle that we bend at. Lambda is the wavelength, we know that, and m is the maximum that we're talking about. So we remember back here, we call this first one m equals 0, the second one m equals 1. So depending on which we're talking about, that's just the value of m. So we're not just required to use that formula, we're also required to derive it. And the way we do that was we do it from this image, and I can tell you that it's a little bit blurry, but basically I'll start here and we'll move to a clearer one. We've got those d is the separation of those slits in the diffraction grating. Theta is the angle we bend at, and yeah, what I'm going to do is I'm going to zoom in on just on this point here. Okay, so we've zoomed in now, and what we've got here is d. That's the separation of two slits. So we can see the light's coming through here, passing through, and the next one passing through. So that distance is the distance between the slits. The angle that they bend is theta. And what we can do is we can create a little triangle here. So what that triangle is we've got our original d separation. That's our distance. And then our light goes through the transmission grating and it bends. All right, if you just kept going with that path, the amount of bends, we label that theta. All right, now there's a mathematical relationship that says if you do that, you can produce the same angle as if you start from the bottom part, meet that top ray at a right angle. If we do that, then this angle here is going to be the same as that top angle. Okay, so what have we created? We've created now a right angle triangle. All right, so that's a right angle triangle. Oops, that's a little bit better. The length of this side is d. This angle is theta. And what we also know is that the difference between these paths is because we're looking at an angle where there's a maximum occurring. And we know that this only occurs when the difference between the path is m lambda. Okay, we've had a look at that last time. That's called the path difference. When this happens, we see a maximum. So what we've got now is a right angle triangle, and we know two sides. We know the opposite and the hypotenuse. Okay, so if we know the opposite and the hypotenuse, SOHCAHTOA sine, our sine of our angle equals the opposite over the hypotenuse. So sine of our theta equals, our opposite is m lambda divided by d. And if we just bring the d to the other side, we get d sine theta equals m lambda. Okay, this derivation is a little bit different than the ones we've been doing, but it's a requirement for the course. Okay, so now another thing we have to look at is the intensity distribution. So we see here down the bottom that we've got what we see when we put some light through this diffraction grating. We've got a really bright spot in the middle, and then going out we've got these different bands. Obviously we're using one color, but what we see with the intensity is if I draw a y-axis that's labeled I for intensity, what we see is that in the middle we have a really high intensity. It's really, really bright, and it drops off very rapidly on the side. Okay, and that basically stays at 0 until we get to the first maximum. Then it peaks up, but not as high. Okay, and the same on the other side, it jumps up, but not as high. Okay, when we get to the second one, again, we jump up, but again, it's a little bit lower, and the same for the third. All right, and that intensity just drops off as we go throughout. All right, so with this intensity distribution, you need to be able to recognize that, draw that it drops off, okay, and show that the overall trend looks a little something like this. We start here, and we just see that smooth decline across. All right, so that's the intensity distribution for this kind of diffraction grating. So let's have a look at an example now. What we've got is a diffraction grating ruled with 4,500 lines every centimeter, and a wavelength of 589 nanometers is used for the grating. What we need to find is the maximum number of orders of reinforcement that can be seen. So how many of these bright fringes are we seeing? The first thing we need to do is work out the distance between each line. So we know that it's 4,500 per centimeter. The way we work out the number of, well, the distance between the lines, we need to work out in meters. So the first thing we do is we write 1 centimeter in meters. So 1 times 10 to the negative 2. And after that, we divide by the total number of lines we see over that point, so 4,500. And that's going to give us the distance between one individual line. And the value we get is 2.22 by 10 to the negative 6 meters. So that's the separation between the line. We also know that the wavelength is 589 nanometers. Nano is 10 to the negative 9. And we want to find the maximum number of orders. So that's going to happen when our angle is 90 degrees. All right, and I'll show you why. So the reason our maximum will occur at 90 is because when we go straight down to the 0th order, we call that 0 degrees. Okay, and as we bend out, we increase that order. Now, if we measure to 90 degrees, it would be along that green line there. Anything beyond that, we're not going to see because you can't bend backwards behind the transmission grating. So that's why our maximum will be seen at 90 degrees. Okay, now we can just plug it into our equation. We've got d sine theta equals m lambda. We want to find m. So if we want to do m by itself, we can divide both sides by lambda. And to substitute in, we've got our d is 2.22 by 10 to the negative 6 times sine of 90, which is 1 actually, so it's going to go away, divided by 589 nanometers. And that's going to give us 3.8, which means we're going to see 3 plus 0.8 of the maximum. Now, if we see 0.8, that means we're not actually getting there. So we always have to round this. So this equals 3 maximum. So we're going to see the third max. All right, so this is part 1. I might just change color. So for part 2, it's asked us what's the number of the total number that we'll see. So we're going to see a maximum of 3 on one side. We're going to see 3 on the other side, and we're going to see the middle one as well. So 3 plus 3 is 6, plus another 1 in the middle. We're going to see 7 total. So we're also able to use this equation to measure wavelength. What we've got here is 6,000 lines per centimeter. So I've just changed that again. So we've got the number. So 1 centimeter divided by 6,000 is 1.67 meters. That's the separation between the slits. We've got our angular position of 47 degrees and our second order image. So m equals 2. So we've got d sine theta equals m lambda. All right, if we want to work out our lambda, we just divide through by m, d sine theta divided by m. And what we get is, if we just put those numbers in, what we get is a wavelength of 609.5 nanometers. All right, so that's all I want to talk about. It was a fairly long video, but hopefully we have learned about transmission diffraction gratings. Thank you.